Hello, everyone, and welcome to the York University Observatory TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'm Sana. I'll be one of your hosts this evening, and I'm joined by Amin, Matt, and Prayosha. We are broadcasting live from the Alan I. Carswell Observatory, located at York University in Toronto, Ontario, Canada. We broadcast every Wednesday night at 7:30 p.m. local Toronto time. If you have any questions or comments on our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. Or if you have any questions about tonight's episode, please put them in the chat and we will answer them live. You can always connect with us on Twitter or Instagram at the handle @York Observatory or on Facebook at Alan I. Carswell OBS. Before we get started with our main show, we wanted to give you a little update on what you can see in the sky this coming week. First up, you can see the planet Mars in the southeast sky. You can also observe Mars with the naked eye, but using even a small telescope reveals some interesting features on the red planet. There is also the open star cluster, the Pleiades, also known as M45, in the east. While you need a telescope to observe most star clusters, the Pleiades is easily visible to the naked eye, even in light-polluted areas. You can see both of these objects all night, so you don't need to stay up too late to observe them. But if you're willing to stay up a little later, you can also observe the peak of the Taurid meteor shower tonight. These meteors will be originating from the constellation Taurus, which is slightly east of the Pleiades, and they come from the comet 2P Encke. These meteors are best observed at around midnight when the sky is darkest, and will appear as bright streaks of light moving quickly through the sky. You don't need a telescope to observe them. Just get as far away from the city lights as you can and look up. So with that update, Prayosha will be starting you off on our presentation, and take it away.
Good evening, everyone. I am Prayosha, and I'm here with Matt, Sana, and Amin, and we are from the Alan I. Carswell Observatory at York University. Tonight, we have got a great presentation about the cosmic microwave background. To get us started, I will tell you all a bit about the historic details. Before we dive into the knowledge of cosmic microwave background, let us outline our journey for the same. The beginning of the presentation, for obvious reasons, ought to be the beginning of our universe. And therefore, the first part will be the Big Bang, in which we will throw lights on the idea, the beginning, and the time before the Big Bang. Later, we will learn about what is cosmic microwave background in more detail, in which we will answer three main questions: what, where, and how. Moving forward, we will sketch the major observations of the cosmic microwave background, and lastly, the importance of the cosmic microwave background along with its path from the past to the future. Well, thinking about how it all actually began is hard to imagine. But in 1927, astronomer Georges Lemaitre said that the universe started as a single point. He added, the universe stretched and expanded to get as big as it is now, and that it could keep stretching. Just 2 years after this, an astronomer named Edwin Hubble noticed other galaxies moving away from each other, as predicted by Lemaitre and other astronomers. And that's not all. The farthest galaxies tend to move faster than the ones close to us. This means that the universe was still expanding, just like Lemaitre thought. And hence, they conclude if things were moving apart long ago, everything would have been close together. Later, the astronomers named this theory the Big Bang and used it as a base to explain how the universe began. Today, we see the Big Bang Theory as being not only a successful model at explaining various models of the universe, but also as correctly predicting the new observations. Although the current instruments do not allow the astronomers to peer back the birth of the universe, they can see the echo of the expansion through the cosmic microwave background. Now that we know what the Big Bang Theory tells us, let us take a closer look at some of its evidence. First is the redshift of the galaxies. We know the galaxies are moving away from us as the light from them is stretched slightly and hence appears a bit redder than it would otherwise do. Next comes the mixture of elements. The composition of new stars differs from the stars that existed 7 billion years ago. The Big Bang theory predicts how much of each element has been made in the early universe. And what we see in the distant old stars and galaxies is just right. Thereafter, we have looking back in time. As known, light takes a long time to travel across the universe. When we look at distant galaxies, we are also looking back in time, and hence, galaxies a long time ago were quite different from those today, showing that the universe has changed. My last point of evidence would be the cosmic microwave background that will be encountered by my friends in the slides later. The video running in this slide is from NASA, giving us an idea about the Big Bang. So, how did the universe begin? Well, it did not occur at a single point as an explosion in space, but instead, it is thought of as a simultaneous appearance of space everywhere in the universe. The evolution of the universe is determined by a tough fight between the momentum of expansion and the pull of gravity. When the universe was born, it was just a lot of hot, tiny particles with light and energy. These tiny particles later group together forming atoms that further group together forming molecules, which led to birth of stars and galaxies. At the same time the galaxies formed, they also began to crash into each other. Also, as the new stars were being born and dying, things like asteroids, comets, planets, and black holes formed. As everything expanded and took up more space, it cooled down to its current state. So, how long did it take? Well, we now know that the universe is 13.8 billion years old. That is indeed a very, very long time. As I mentioned before, ever since the Big Bang, space has been expanding. It is an intrinsic expansion whereby the scale of space itself changes. It is finite in both time and space. There are three possible types of expanding universe: open universe, flat universe, and closed universe. And each type of universe will have its own ultimate fate. If the universe was open, it would keep expanding forever. If it were flat, it will also keep expanding, although the expansion rate would slow down to zero after an infinite amount of time. If the universe were closed, it would eventually stop expanding and recollapse on itself, which will possibly lead to another Big Bang. Hence, to conclude, the Big Bang is not an explosion of matter that is moving outward to fill an empty universe. Rather, space itself expands with time everywhere and goes on increasing the distance between objects, current galaxies. Now I would let Matt take over and explain to us the cosmic microwave background in detail.
Well, thank you for that interesting explanation about the Big Bang. But how does it relate to the cosmic microwave background, or CMB? Well, basically, the cosmic microwave background is seen as the leftover radiation from the Big Bang itself. When the universe was born, it underwent a rapid expansion called inflation. And we know from thermodynamics that all this energy from expanding has to be transferred somewhere, right? Well, in this case, the energy transformed into heat. This heat is an electromagnetic radiation remnant of the early stages of the formation of our universe. It is also called relic radiation. This radiation is extremely faint, but covers all space. And yes, you guessed it, this radiation is the cosmic microwave background. As I just mentioned, the cosmic microwave background is the direct consequence of the formation and specifically the expansion and inflation of our universe. But first, we have to take into account that in the early formation of the universe, the temperatures were extremely high if we compare them to how it is nowadays, of course. What does this have to do with the cosmic microwave background? Well, essentially the fact that it takes back to about 400,000 years after the Big Bang. Back then, the universe was 100 millionth the size it is today. So not only everything was more packed, but temperatures were as extreme as 273 million degrees. Any atoms present at the time were quickly broken apart into protons and electrons because of this, and particles of lights and other radiation were scattered off the electrons during this time. Once the universe started expanding more and more and cooling down, particles were able to form atoms. And this remnant radiation from the Big Bang was able to travel without colliding with these particles, leading to the cosmic microwave background. Well, the cosmic microwave background. First, the question: how was it discovered? It was actually discovered. It was found by accident in 1965 when two researchers with Bell Telephone Laboratories, Arno Penzias and Robert Wilson, were creating a radio receiver and were puzzled by the noise it was picking up. They soon realized the noise was coming uniformly from all over the sky, not to be mistaken with the radiation emissions coming from the center of our Milky Way, which was also discovered by accident by the Bell Laboratories. At the same time, a team at Princeton University, led by Robert Dike, was trying to find the CMV, or cosmic background. Dike's team got wind of the Bell experiment and then realized the CMB had been found. Both teams quickly published papers in the Astrophysical Journal in 1965, with Penzias and Wilson obviously talking about what they saw and Dike's team explaining what it means in the context of the universe. Later on, Penzias and Wilson both received the 1978 Nobel Prize in Physics because of this. Now, I've mentioned before that the CMB is essentially heat. In other words, it is a temperature. But can we humans actually feel it? Well, the answer is no. You can see the CMV with your naked eye or feel it, but it is everywhere in the universe. It is invisible to humans because it is so cold. It is actually, in fact, just 2.725 degrees above the absolute zero, which is minus 459.67 degrees Fahrenheit or minus 273.15 degrees Celsius. This means its radiation is most visible in the microwave part of the electromagnetic spectrum. With a traditional telescope, the space between the stars and galaxies, meaning the background, is completely dark. However, a sufficiently sensitive radio telescope shows a faint background noise or glow, almost isotropic, that is not associated with any star, galaxy, or other object. This glow is the strongest in the microwave region of the radio spectrum, and that is how we derive and detect the temperature of the CMB. With the help of Sana, we'll understand not only how to detect it, but how to observe it properly and what are the tools we have so far to study this.
Thank you, Matt. Now that we know what the CMB is and how it was first detected, let's talk about some of the most important observations since its detection. The CMB is observed using microwaves and radio waves, so many modern observations of the CMB are made using space telescopes. This is because, while it is possible to observe the CMB from the Earth's atmosphere blocks a lot of radio waves, making some observations impossible. So putting telescopes in space above the Earth's atmosphere allows for a broader range of radio waves to be observed and more precise measurements to be made. There are 3 satellites that made critical observations of the CMB: COBE, WMAP, and Planck. The first satellite we'll look at is COBE, or the Cosmic Background Explorer. COBE was launched in November of 1989 and operated until 1993. It took precise measurements of the CMB covering the entire sky, generating the map shown on the right of the slide. This map shows the temperature of the CMB across the whole sky, with different colors indicating different temperatures. While the map might look like it has massive temperature variations, it is important to note the scale the map is using, which shows variations on scales of as small as a fraction of a degree. So as mentioned before, the CMB only has very tiny variations in temperature. At the time, Kobe provided the most precise measurements of the CMB ever taken, measuring its spectrum with a precision of 0.005%. Kobe's measurements were used to confirm the Big Bang theory and also began a new era of cosmology with precision measurements. In fact, Kobe's measurements were so groundbreaking that two of the scientists on the mission, George Smoot and John Mayer, received the Nobel Prize in 2006 for their work. After Kobe, the Wilkinson Microwave Anisotropy Probe, or WMAP, was launched in June of 2001 for what was initially supposed to be a 2-year mission that turned into a 9-year mission. It obtained even more precise measurements of the CMB than Kobe, generating temperature maps with a higher resolution than its predecessor, and made some other important measurements. Among them, WMAP determined the age of the universe to be 13.8 billion years old. It measured the composition of the early universe and showed that the first stars formed 500 million years after the Big Bang. In 2009, the European Space Agency launched the Planck satellite, which would go on to measure the CMB in even greater detail than both Kobe and WMAP, providing the most detailed image of the CMB ever obtained, shown on the right of the slide. This image on the left shows the same patch of the CMB image through all 3 satellites and shows how much the resolution of the map improved with each satellite. In addition to this map, the Planck satellite provided new measurements on the current composition and age of the universe and measured Hubble's constant, which determines the rate of expansion of our universe with incredible precision. While you need space telescopes to get precise measurements of the CMB, it turns out that you can also see some of it from your own home. If you have ever seen static on analog televisions, you have in fact seen a very small amount of the cosmic microwave background. This is because old analog televisions are tuned to detect radio waves, which are used to display a program on the screen. Static on the screen is caused by random radio waves that are coming from a variety of different sources, and since the CMB is radio waves, the television will detect some of them along with other sources of static. The CMB is not responsible for all the static noise, though, accounting for only about 1% of the static you see on analog televisions. Now Amin will talk about why studying the CMB is important and how it has influenced our understanding of the universe.
So why is the cosmic microwave background important? The CMB is direct evidence of the Big Bang model of the early universe. It is the oldest electromagnetic radiation we can see, which means it can provide a lot of important information about the early universe. This information is critical for our models of the early universe and for the field of cosmology, which is the study of the origin and development of the universe. Without the CMB, we would only have different theories about how the universe developed in its early history. It is a crucial piece of evidence alongside the discovery that the universe is expanding. The CMB can be seen everywhere in space, and it is redshifted into the microwave range. This redshift must have taken a very long time, and because it's everywhere, it confirms that the CMB is directly linked to the structure of the entire universe at a very early period of its development. The CMB shows the afterglow of the Big Bang. It comes from a predicted period early in the history of the universe where the universe became transparent to light, releasing a lot of photons everywhere in space. The Big Bang model predicts this release. As the universe expanded, it must have become less dense. Beginning opaque, it eventually expanded enough to release all the trapped up light that previously could not escape. We can see the CMB in all directions, and it appears to be very uniform. There are barely any temperature discrepancies between parts of the spectrum. This suggests that the early universe was almost the same everywhere, containing a lot of dense materials. The temperature differences in the CMB actually correlate to the positions of clusters of galaxies in the universe. As the universe expanded, some places had more of a concentration of mass than others. These regions later became the galaxy clusters, and they can be seen as slightly hotter regions in the CMB. All of these things contribute to the success of the Big Bang model. Now we'll discuss the history of the universe. Because the universe is expanding, it must shrink the further you go back in time. As discussed earlier, the CMB is direct evidence that this expansion has been going on since the very early stages of the universe, confirming the Big Bang model, which posits that the entire universe was once concentrated in a much smaller volume of space than now, and that rapid expansion occurred until the universe as we know it today evolved. Theoretically, you might imagine the shrinking of the universe as you go backwards in time could continue all the way until the universe becomes contained in a single point. This is called a singularity. We cannot necessarily actually predict this, however. As the universe becomes denser and denser, the level of energy gets so intense that physics as we know it might change. We need to conduct more experiments in particle accelerators to confirm that physics still works the same in higher energy conditions. Also, once the universe becomes smaller than something called the Planck length, lacking a theory of quantum gravity, we do not know what would happen on scales that small. So how did the universe originate? One theory says that there was a singularity and the universe expanded out from it. Time and space both began at the singularity according to this theory. We discussed this in the last section. There was no before the singularity. An analogy can be made. If you head north on Earth and go the right direction, you will eventually reach the North Pole. Once there, you cannot go further north. At the North Pole, every direction heads southward. Everywhere on the Earth is south of the North Pole. Similarly, the singularity theory says that every when in the universe is after the singularity. Others believe that there may have been another universe, perhaps with different features and laws of physics, which collapsed into a small volume and expanded outward again. This kind of big crunch, as it is called, might happen over and over again in cycles. Perhaps that is the future of our universe too, a collapse and subsequent expansion. What do we know about the fate of the universe? There has been some discussion of this topic earlier in the presentation. The Big Crunch is one model. Another theory is the heat death of the universe, which posits that the universe will continue to expand until all energy differences dissipate and the universe freezes into nothing forever. This is quite bleak. The Big Rip theory says that the expansion of the universe will be so great that everything, even the smallest particles, will be ripped apart. There are other theories, but these three are the main ones. The geometry of the universe is very important when it comes to its fate. Depending on the shape, the fate can be predicted. The CMB can provide evidence for what the shape is. Measurements show that the universe appears to be flat, which would imply the heat death theory. The CMB can help with conducting such measurements. As humans, we are interested in knowing more about the world around us. We are curious about our ultimate origins and our future fate. Studying the cosmic microwave background can give us a lot of crucial information which may solve the biggest mysteries in the universe. This concludes our presentation on the cosmic microwave background. What do you think? Do you think the universe will expand forever or collapse back into itself?
Well, this is Professor Hyde just lurking in the background. I think I would guess that the universe will probably expand forever. That is one of our favorite questions. Anyone else have a favorite answer?
My guess would also be that it would expand forever, but part of me wants to believe that the Big Crunch model is correct, because it would just kind of be interesting to have a universe that kind of never ends, where it just keeps repeating.
I absolutely agree. It's a very appealing idea to think of that the universe might be a never-ending cycle of universes. But given the speed that the universe seems to be expanding now, it does seem like it might just keep going forever and ever, which would lead to, of course, the cold and icy, lonely future when all the stars eventually go dark. So it's a little bit more of a Twilight Zone ending to the universe, I suppose.
If you have any comments, feel free to put them in the chat.
I don't have a favorite theory, actually. I think we need more information because we only see a limited part of the universe based on how much time there's been for light to reach us. So I'm inconclusive on this one.
That's actually a very scientific answer. So that is a very good point. We are actually only seeing a small portion of the universe due to this accelerated expansion and the limited speed of light. We can only see a fraction of what must be out there. I think this is a wonderful question and perhaps something for folks to ponder in the recorded version. It doesn't look like there's too many favorites coming through on chat, but we did get one little extra question coming in, which is if the CMB is leftover radiation, is that the same thing as light? And this is actually a fun one to maybe add into our broadcast. Is it the same thing as light?
So if I'm understanding the question correctly, when a lot of times when physicists or astronomers say radiation and light, they use them kind of interchangeably, because radiation is is electromagnetic radiation, and what we see as light is just a very small range of the electromagnetic spectrum. I can't recall what exactly the wavelength or frequency of that light is, but it's just a very small portion of the electromagnetic spectrum. And all the cosmic microwave background radiation is radiation that's at longer wavelengths than we can see. It's radio waves, and those are the very far end of the wavelength scale, so they can get quite long. But physicists and astronomers do use that light and radiation interchangeably. So I think the answer to the question is yes, it is the same thing as light, but just not light that we can see.
Exactly right. I think that's a wonderful answer and probably a good wrap up for today's show. Sana, you want to transfer over to the outro?
Yes. Okay.
Well, everyone, you have been listening to the Alumni Crystal Observatory's weekly TeleTube broadcast, the Astronomy and Astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Matt, Prayosha, Suna, and myself, Amin. Make sure to leave any comments or questions in the comment section of the video, and we'll be answering them in the next 20 minutes or so. All of our programs are free, but if you'd like to make a donation, see our website at observatory.info.yorku.ca. You can always connect with us on Twitter with the handle @YorkObservatory, and check out our website for show notes, content, updates, and contact info at observatory.info.yorku.ca. Thank you for tuning in. Clear skies and have a good night.